Okay, we got a couple more Atwood problems here. These are going to require us to look back at our kinematic equations. So just a refresh on those because it's been a while. So remember, these were our equations we used throughout the first unit where we connected initial, final velocity, acceleration, time, and displacement together. And we said if we have three of those, we can solve for the other two using these equations. And these can be used in connection with dynamics. We haven't talked about that a whole lot yet, but you can, if you've got an accelerating system, I mean, these same things apply, right? So we're going to look at just a couple of examples of that. So here's an Atwood machine. We've got two blocks. We've got an M1 of 3 and an M2 of 2. And they're held at rest and then released at 0 seconds. And we want to know the speed or velocity of the 3 kilogram block at 2 seconds. So keep all that in mind. Okay, so things that we've got here. We're at rest, so our initial velocity would be 0. Time is 2 seconds, because that's the time we're interested in. And then we want to know our speed at that time. So we want to know a final velocity at 2 seconds. We can figure out acceleration because we know how to do that for an Atwood machine. This was our equation. So if we get acceleration, then we've got 3 of these quantities, and we can put those back into, whichever one of these makes the most sense and solve for final velocity. Okay, so let's get acceleration right quick. 9.8 times 3 minus 2 divided by 3 plus 2. So that's basically 9.8 divided by 5, which gives me really right at 1.96 meters per second per second. Okay, so just subtract them on the top, add them on the bottom. So now I have acceleration, I have initial velocity, I have time, I want final velocity. I'm going to go with the first equation because it looks like the easiest and the cleanest way to do it. So solving for final velocity equals 0 because I was initially holding these at rest and then let them go, plus 1.96 acceleration times time is 2, and that's going to give me roughly, approximately, I got 3.92 meters per second when I multiplied those, and that's closest to the answer of 4 over here. Okay, so that's one way you can take information you get from a dynamic situation where you've got an object accelerating and then connect it to kinematics that we've talked about before. So let's look at another example of that. Let's see, I'm trying not to cover up all my kinematic equations, but I'll just go back to them. So now we've got 100 kilogram block, and we don't know this mass. We're told that this takes 6 seconds to reach the floor after being released from rest. What is the mass of the block on the left? Okay, so we are solving for a mass here, which is a little different than what we've been doing. Let's think about some of the things that we know. Okay, we know M1 is 100. We know that time is 6 seconds. We're released from rest, so we got an initial velocity of 0. we see that we're going to reach the floor. So it appears we're going to travel a displacement of 1 meter based on this picture. They don't tell us that, but I think that that's what they want us to assume based on this also being a given. Okay. So the first thing I think we need to do is try and get acceleration using our kinematic equations, because we don't have this mass. So we can't use our acceleration equation. But if we get acceleration, we can put it back into this equation and solve for this second mass. Okay. So let's look at our givens. We've got time. Oops, sorry, I have to go back and forth. We've got time. We've got initial velocity. We've got displacement. We want acceleration. So let's look at these. Okay, so we need one with displacement. We need one with time. Because we don't really have a final velocity value. So probably this one is the one I'm thinking of using. Because this goes away and we have that and we have time. So let's try that one. So I'm going to rewrite it down here. Displacement equals VIT plus 1/2 AT squared. This goes to 0. This is 1 meter from my diagram. 1 equals 1/2 times A, I don't have that, times 6 squared. Okay. I'm gonna shift this fraction over to the other side. So I've got 2, and then I'm going to square 36. So I've got 2 equals 36 times A. And so when I solve for A, I'm going to end up with 0.056 meters per second. So it's a small acceleration value. It is taking it an entire 6 seconds to reach the floor. So I don't know. Hopefully that makes sense. I think it does. So now I'm going to use A equals G times M1 minus M2 divided by M1 plus M2 to get M2. And this is going to look a little messy, but it's really just algebra at this point. So I've got my acceleration I solve for equals 9.8 times 100 minus M2, because I don't have M2, over 100 plus M2. Okay, I'm going to take this over to the other side. I guess I'm basically multiplying both sides by this expression. So I've got 0.56 times 100 plus M2 equals, and I'm going to go ahead and distribute this 9.8 just to clean this up a little bit. So I'm going to have 980 minus 9.8 times M2. Then I'm going to distribute over here as well this 0.056. So that's going to give me 5.6 plus 0.056 M2 equals 980 minus 9.8 M2. Then I'm going to combine like expressions. So like I want to put this 5.6 over with the 980. That's going to give me 974.4, because I'm going to subtract that from both sides. And then I'm going to move this 9.8 times M2 over here to go with the other. So my two expressions with M2 are together. So I'm going to have 9.856 M2 on the other side. I'm just taking this and moving it over. When I do that, this negative sign changes and I'm adding 9.8 and 0.056. And then I'm going to divide both sides by 9.856, and I end up with M2 equals 99 kilograms. So these two masses are almost the same. This one's only a little bit smaller than this one. And I think that makes sense based on the small acceleration value, because this one's able to move because it's larger, but it's only just barely. So it's going to move pretty slowly because this one's pulling, you know, with almost the same force of gravity on the other side. So, anyway, but that's a couple of examples of how you use dynamics and kinematics combined together.